So many of you have written to me asking whether networking is a key hacker skill. The unequivocal answer is yes. You are very unlikely to be successful in this field without a fundamental 13 PAGE understanding of networks and networking. As a result, here is my network basics for hackers. To help you get started. IP addresses. Internet protocol addresses, IP addresses make the world go round. Or at least enable us to. Email, Zoom, watch YouTube videos, tweet, and navigate the web. It's almost as important as the world going around. Each digital device, computer, laptop, phone, tablet, etc., is assigned an IP address, and this is what enables us to communicate and connect with it. Imagine an IP address as being similar to your house address. Without that address, no one could find you and send you snail mail. The IP address system we are presently using is known as IP version 4 or IPv4. It is made up of 32 bits of 4 octets, 8 characters, or 4 groups of 8 bits on-off switches. Take, for instance, 192.168.1.101. Each of the numbers between the dots dot symbol is the decimal equivalent of 8 bits. This means that we calculate the base 2 number that computers use, represented by the 8 bits, and convert them to decimal numbers that humans are more accustomed to working with. See the diagram below. Each one of the octets, 8 bits, is capable of representing numbers within the range 0 through 255 2 to the 8th power. IP addresses are generally put into 3 classes, A, B, and C. The ranges of the classes are as follows. Class A, 0.0.0.0.127.255.255.255. Class B, 128.0.0.0.191.255.255.255. Class C, 192.0.0.0.223.255.255.255. In Chapter 2, we will address subnetting and subnet masks that vary with these different IP classes. Public versus private IP addresses. It's important to note that our IP address system has its limitations. The most significant restraint is that there are not enough IP addresses to cover all devices that need to connect to the internet. The IPv4 system we are working with now has only 4.3 billion IP addresses. With 7.5 billion people on the planet and far more devices, that certainly is not enough. As a result, a system was developed to reuse a group of IP addresses within a LAN that are not usable over the internet. These addresses can be used over and over again within each local area network, but not over the internet, thereby conserving the number of IP addresses necessary to keep the world going round. These private addresses include 15 PAGE, 192.168.0.192.168.255.255, 10.0.0.0.10.255.255.255, 172.168.0.172.168.255.255. You have probably seen the private IP addresses beginning with 192.168.xxx.xxx or 10.xxx.xxx.xxx on your Kali system when you type ifconfig. This is your private IP that is only usable on the local area network. To communicate over the internet, your IP address must be translated to a public IP by NAT device, see NAT below. Dynamic Host Configuration Protocol, DHCP, assigns IP addresses dynamically. This means that you do not have the same IP address all of the time. Most of the time, these IP address assignments are on a local area network. Remember, on LANs, we use private IP addresses. When each device is connected to the LAN, it must request an IP address. That device sends the request to the DHCP server that assigns an IP address to that system for a fixed length of time, known as a lease. 16 PAGE. Each time you connect to the LAN, you are likely to receive a different dynamic IP address, but usually in the same range. For instance, 192.168.0.0, 192.168.255.255. Network Address Translation, NAT, is a protocol whereby internal private IP addresses are translated to an external public IP address that can be routed through the internet to its destination. Remember, private IP addresses of the systems inside the LAN cannot use their IP addresses on the internet because they are not unique. Every LAN uses basically the same IP addresses inside their network. The NAT device accepts requests to traverse the internet from an internal machine. It then records that machine's IP address in a table and converts the IP address to the external IP address of the router. When the packet returns from its destination, the NAT device looks into the saved table of the original request. It forwards the packet to the internal IP address of the system that made the original request within the LAN. When working properly, the individual systems and users don't realize this translation is taking place. For instance, the diagram above shows 4 computers with private IP addresses behind a device that is serving as both a NAT device and a router. Not uncommon. The devices use their private IP addresses within the LAN, but when they want to communicate over the internet,
ports are a kind of sub-address. The IP address is the primary address, and the port is the sub-address. Using a well-worn but effective metaphor, think of the IP address as the street address of a building, and then the port as the apartment number. I need the street address to get to the correct building, but I need the apartment address to find the individual person. This is similar to ports. The IP address gets us to the right host, but the port takes us to the proper service, say HTTP, on port 80. There are 65,536 squared, 2 raised to the 16th power, ports. The first 1,024 are generally referred to as the 65th port, common points. Obviously, people don't remember all 65,536 ports unless they are savant, or even the 1,024 most common ports. As a hacker, security engineer and/or network engineer though, there are a few ports that you should know by heart. We can use a tool such as Nmap to see what ports are open on a system. In this way, the security engineer or hacker can see what ports are open and which service is running on the target system. For instance, to see all the ports open on a Metasploitable-2 system, an intentionally vulnerable Linux system developed by the good people at Metasploit, we can run the following command: Kali greater than sudo mmap-s t less IP address of the target system greater than. Map then reports back with the open ports and the default service on that port. Next, I want to introduce you to the basics of TCP/IP, i.e., Transmission Control Protocol, TCP, and Internet Protocol, IP. These are the most common protocols used on the internet for communication. To become a proficient hacker, forensic investigator, or simply a good network engineer, you should understand the structure and anatomy of these protocols. From my experience, many professionals it's not like you were interrupting with other people. It's not like a single bad fantastic Facebook thing, but it's also interrupting with other people. The companies that consider the last part of the matter have no pressure and fear about the facts. It's also interrupted we're interrupting with other people. It's also interrupting with other people volunteering their breakthroughs, which means that they feel less pressure and less intent. Protocols in their fields is essential. Otherwise, you will simply be wasting your time. What are protocols? Protocols are simply an agreed-upon way to communicate. For instance, we here on Hackers Arise have agreed upon the English language with all its rules and grammar as our way to communicate. That is our protocol. If we did not have an agreed-upon way to communicate, people would be using many languages, grammar, and rules, and none of us would understand each other. Protocols are similar. A protocol simply defines a way of communication with all its rules. These rules are usually defined by an RFC, request for comments. There are many protocols in use on the internet. These include TCP, IP, UDP, HTTP, STP, MSTP, and so on. And each has its own set of rules that must be complied with to communicate. Effectively, similar to the RU, but with a capital R. IP, Internet Protocol, or Internet Protocol, is the protocol that is used to define the source and destination IP address of a packet as it traverses the Internet. It is often used in conjunction with other protocols, such as TCP, hence the often used conjunction TCP/IP. Let's look at an IP packet header and see what information it contains that can be useful to the aspiring hacker and/or forensic investigator. Row 1. Version. This defines the version of IP, either v4 or v6. IHL defines the header length. Type of service, TOS. This defines the type of service of this packet. These include minimize delay, maximize throughput, maximize reliability, and minimize monetary cost. Single, total length. This defines the total length of the IP datagram, including the data, or the fragment. Its maximum value is 65,535. Row 2. Identification. This field uniquely identifies each packet. It can be critical in reassembling fragmented packets. IP flags. This field defines whether the packet is fragmented, M, or not, D. The manipulation of the field can be used to evade IDS and firewalls. Check out my tutorials on Nmap and HPN3 on how we can manipulate packets to evade intrusion detection systems and other security devices. It can also be used in conjunction with the window field to identify the operating system of the sender. Row 3. TTL. This is the pack. Time to live. This defines how many hops across the internet before the packet expires. It varies by the operating system, making it helpful to identify the OS of the sender. Protocol. This field defines what protocol is being used with IP. Most often it will be 6 or TCP, 1 for IMCP, 17 for UDP, among others. Right under that, header checksum. This is an error checking field. It calculates the checksum, a simple algorithm, to determine the integrity of the data in the header. Rows 4 or 5. Source/destination. These rows of the IP header are probably the most important part of the header, as it contains the source and destination IP address. Row 6. Options. This field is variable in length, and its use is optional, as you might expect. Padding. This field is used to fill out, if necessary, the remaining bits and bytes of the header. In the TCP header, there are numerous critical fields that the aspiring hacker and/or forensic investigator should understand. 23 vertical bar P, A, E, G, E, row 1. Source port, destination port. Probably most importantly, these are the source port and destination port. These fields determine what port the communication came from, source, and where it is going, destination. Row 2. Sequence number. The sequence number is generated by the source machine's TCP stack and is used to make certain that packets are arranged in the proper sequence when they arrive. It is also important in defeating MIT-M attacks. Row 3. Acknowledgement number. This is an echo of the sequence number sent back by the AMZ receiving system. It basically says, I received the packet with the sequence number. In this way, the sender knows that the packet has arrived. If the sender does not receive an acknowledgement number back in a fixed amount of time, it will resend the packet to make certain the receiver gets the packet. In this way, TCP is reliable. In contrast, UDP does not do this and is therefore unreliable. Row 4. The fourth row has some critical information. Let's skip over the data offset and the reserved fields. That takes us to 8 bits near the middle of row 4. These are the infamous flags of the three-way handshake and Nmap scans. The first 2 bits, CWR and ECE, are beyond the scope of this lesson. The next 6 bits are the ERG, AC, PSH, RST, SYN, and FIN flags. These flags are used by TCP to communicate. SYN, the opening of a new connection. Financial, the normal, soft closing of a connection. Acknowledgement of a packet. All packets after the three-way handshake should have this bit set. Relative timestamp, the hard close of a connection, and is usually used to communicate that the packet has arrived at the wrong port or IP. URG, this flag indicates that the following data is urgent. PSH, push the data past the buffer to the application. If you are familiar with Nmap or HPing3 as recon tools, you have used scans utilizing all of these flags. By creating packets with flag combinations that should not be seen in the wild, we may be ability to elicit a response from a very secure system, or even evade detection. Right side of window size. In some diagrams, this is simply described as the window field. Its role is to communicate the size of the window that the TCP stack has to buffer packets. This is the way that TCP manages flow control. From a recon or forensics perspective, this field alone can be enough to identify the OS that sent the packet. Row 5. Checksum. This field uses a simple algorithm to check for errors. In essence, it is an integrity checker. URG. Pointer. This field points to the last byte of the sequence number of urgent data. The URG flag must be set in conjunction to activate this field. Row 6. Options. Like the IP header, the TCP header has an options field to be used if necessary, and it has varying length. Padding. The padding is necessary to bring the TCP header to a multiple of 32 bits.
TCP three-way handshake. Every TCP connection starts with a three-way handshake. The handshake begins with a client sending a packet with the SYN flag set saying, "Hello, I want to talk to you," the server responds with a packet with the SYN and ACK flag set saying, "Hi, I'm willing and able to chat," and 25 PAGE. Then finally, the client sends a packet with the ACK flag set that acknowledges the response of the server, and then the data transfer can begin. UDP. User Datagram Protocol or UDP is a connectionless protocol, versus TCP, which is connection-oriented and requires a connection such as the three-way handshake as seen above. It is more lightweight than TCP since it doesn't have the overhead of assuring a connection and making certain that each packet arrives. UDP simply sends packets and forgets about them. This works great in applications where you want efficiency and no one packet is critical, such as streaming music or video. Some of the key protocols that use UDP include DNS, only for queries, SNMP for network device management, and NTP for network time synchronization. When scanning for UDP ports with tools such as Nmap, it can take a bit longer as UDP does not have a response for lost packets or closed ports. Nmap simply waits a specified time, and if no response is returned, it assumes the port is closed. You can scan for UDP Nmap with the following command. Kali Nmap SU. Network topologies. When devices are connected together, there are several options for the physical layout of the devices. This physical layout can be very important in optimizing the distance, latency, congestion, and availability of any two nodes on the network. This physical configuration is known as topology. Ring topology. The original topology in the early systems was a bus topology. Each of the devices is strung together in a single line. Each device can tap into the bus to send and receive packets. Every node can see every packet sent over the bus. Each device has to examine each packet to determine if the packet is intended for them. The advantage to the bus topology is that it is cheap and simple, while the disadvantage is that on a busy network, it can easily become congested. Star topology. The star topology is the most popular topology for local area networks, LAN. In the star topology, there is a server at the center of the star, and the clients all connect to the server. The advantage of this topology is that the connections to each of the clients are independent, and if one client or its connection is broken, the other's clients can still communicate with the server. Ring topology. The ring topology sends the packets around a ring, and only the client the packet is intended for can grab the packet from the ring. The advantage of the ring topology is that it is simple and inexpensive, but if the ring is broken, all clients cannot receive any communication. Mesh topology. The mesh topology has many connections between each device on the network. This means that a packet has a variety of paths to take to its destination. This gives the network resiliency in the case that one cable or path is broken. This is similar to how our modern internet is connected. Packets have multiple paths they can take to the target system. The OSI and the TCP models are the most common models to understand the way that these various protocols work together. Many novices tend to minimize the importance of these models as they initially don't seem to have any practical importance to networking systems. In reality, you should at least have a basic understanding of these models, as you will hear references to them repeatedly in your career, such as, "This is a layer 3 switch." This would be unintelligible without a rudimentary understanding of the OSI model. Let's begin with the OSI model. The diagram below displays the 7 layers and the basic use of that layer in network communication. As you can see, there are 7 layers to the OSI model: the application layer, the presentation layer, the session layer, the transport layer, the network layer, the data link layer, and finally, the physical layer. The figure above details the various layers and the protocols and activities associated with each. To help you remember the various layers of this model, there are at least 2 mnemonic devices to help. If we start from the top and work our way down, we can take the first letter of each layer, namely, A, P, S, T, N, D, and P. Many people remember these layers by using the mnemonic device. All people seem to need data processing. If you remember that phrase, you can likely remember the various layers. If we work our way up the model, we get P, D, N, T, S, P, and A. Then we use the phrase "Please don't throw sausage pizza away." Feel free to use either or make up your own. The key is to remember the 7 layers. I hope this helps. The attacks against the protocols in this model can be categorized as follows. 30PAGE. The application layer generally includes applications such as a browser, word processors, and other applications. This layer's most important attacks are likely to be exploits. These are attacks that can often embed the hacker's code within the application to take control of the application and the system. At the presentation layer, the most concerning attack is phishing or sending emails to various people with malicious links. At the session layer, the most important attack is hijacking. Hijacking is where an attacker can take over an existing session established legitimately by the user. At the transport layer, the hacker often does their reconnaissance at this layer. At the network layer, the attackers can conduct man-in-the-middle (MTM) attacks where they place themselves between a legitimate user and a server, thereby eavesdropping on the traffic and possibly even altering it. At the data link layer, the attacker can spoof the MAC addresses, the globally unique address. Stamped on every network device and essential to the proper functioning of a LAN, see ARP. Finally, the physical layer can be attacked using sniffing. Sniffing is the practice of watching and analyzing network traffic, see Wireshark and sniffers in Chapter 4. We will look more closely at each of the attacks against the network protocols and layers as we proceed through this book.